Okay, welcome to the next and in fact the last video in this systems programming video series. And it is going to be the last video, even though there's maybe kind of a lot to talk about. Maybe I ought to be reading the textbook and doing the programming assignment with some additional, detail and care. But the thing is, as I record this, the school semester is getting going, and I am really struggling to try to stay on top of this stuff while I'm also, the rest of my work is really ramping up. And so I'm just going to speed run, sprint to the end of this thing. And I think luckily, kind of covered a lot of the stuff that is needed to be able to do that. So I'm not going to read chapter 12 or do any of the other stuff. I'm just jumping right into assignment 10. And almost all of assignment 10 seems to be, there is this thing about the Buddha brought, and I think that's maybe just like implementing a slightly more sophisticated way of coloring the Mandelbrot thing, but that's not the right? Like maybe not the most interesting part of this for computer science. So really, I think what the most interesting thing here is for computer science is implementing a multi-threaded version of the thing that we did last time using pthread. And therefore, that's all I'm going to do. And I'm going to wrap up this video series so that I can really spend the rest of my time on money making things. So to get into that, and again, because I am now going really fast and just trying to kind of sprint to the end, I am no longer going to walk you through the thought process and like my process of building. Instead, I'm just going to show you right here the thing that I built. I'll explain what's already here, but yeah, I am not going to be quite as uh, thorough, I guess, um, as I have been in perhaps other videos. So here I'll just get into explaining everything. So for the read ppm file, I just copied over exactly the same read ppm thing that was written several assignments ago and used in the previous assignment. The only other thing that I'm going to edit here is the thread Mandelbrot file. A lot of the header information was already given. We've already written the populate region function in the previous assignment, but because we're going to use threads, then this time the function needs to take only a single argument because kind of pthreads is only set up to give a function, like sort of a multi-threaded function, uh, basically just a single argument, and the argument must be a pointer. The design and a void star pointer, right? Like basically like an untyped pointer kind of. So the design here is so that through this single argument, you can build a struct, which itself is just a bundle of all of the arguments. So you'll see here that where in the previous function I used to have these many arguments, all as an argument to the populate region function, they're now all packed into a struct. So all of the upper left row, upper left column, so on, that used to be an argument to the function is now packed into this struct. All the xmin, xmax, and all the other things are packed into a struct. It may be worth pointing out that my pix map is a pointer, right? A ppm pixel pointer. And the palette is also a pointer, but the black pixel is not a pointer. That was just a sort of hard-coded single struct. And so that doesn't get a star here. Now, to adjust the function, of course, I pass in the args because I'd like to do, in some sense, as little thinking as possible here. Then what I prefer to do is to sort of cast my untyped void star pointer into an arg struct pointer, and then sort of unpack everything so that my variable names are now exactly what I had before, right? That way I don't have to edit any of the code that I wrote previously. I simply just kind of unpack everything from the arg struct into the same names as what I had before, and now everything just works as it did before. And so all this implementation here is the same as usual. It is worth remarking that when you do pthreaded, you use the pthread library, you will need to have this function that the thread executes return a void star pointer. And so, but I don't want that return value, right? So it has to be there for the compiler, but I don't really want to use it, so I just return null. Okay, in the main function, a lot of this stuff was distributed by the class, so not much to talk about there. It's supposed to have an optional number of processes. I'm just going to ignore that entirely. Um, it wouldn't be hard to adjust what my solution here so that you did have a variable number of processes, but again, I'm just in a sprint at the moment. So I'm just going to just hard code that it's going to run 4 processes. Okay, down here, we malloc space for the pixel map. We malloc space for the palette of colors. This is all exactly as it was in the previous assignment. And then here we finally get to pthreads. So I declare 4 threads, T1, T2, T3, T4. I malloc enough to make an arg struct, right, for my arguments. Although, ooh, that's interesting. Oh, I'm just now noticing that they're like kind of out of order, and I'm not sure how that happened. But in any case, it seems like everything is perfectly fine. It's just in an order I didn't expect it to be in. But okay, fine. So the basic idea here, so I guess we'll just start with 2 since it's up at the top, is that I go ahead and create this arg struct with arguments, so that my upper left corner of the region of the pixel map that I'm going to populate is row 0, column 1/2 of the pixel, or the pix map. And lower right corner is all the way to the right end, or sorry, yeah, all the way to the right and no, halfway left, right, all the way down. So anyway, point is just that this should fill a portion of the pixel map, basically like 1/4 of the pixel map. I probably didn't write these in the most like in the sequence that is easiest to read or think about, but if you want to clean it up on your own end, you can certainly do that. So anyway, and then we just put all the other values where they need to go, and that is A2. So that's going to be basically the arg struct used for the second thread. Okay, A3 is very similar for the third thread, fourth thread, and the first thread. Down here, we go ahead and create each of these threads. So you give it the address of the thread. You give it this null pointer, which I think, I don't know too much about this, but I think it's basically like, sort of specific features of the threaded process that you may want to have, but they're not going to be interesting for us, in this assignment. So there's no need to worry about that. It just needs to be there for the compiler. Give it the name of the function, which we have up above, and we just talked through a bit. And then give it the arguments that are fed to that, or well, really the one argument that is fed to that function. And as soon as you call create, the process, the thread, is now running. So as soon as I called that, this thread is running. While they're running, right, they're running in parallel, meaning like they execute at the same time, right, on a single pulse of the CPU. Instructions for it and any other thread in existence are being computed with shared resources on a single pulse. that is in contrast to other kinds of concurrency, like we did in the previous assignment. So you should probably expect this to run a little bit faster because in the previous assignment, any gains that we got in speed, and we did see that there were gains, but what that must have been, I think, is that because it wasn't multi-threaded, right? It was it was concurrent because it had multiple processes, but it was not multi-threaded. And so why would you see any gains in speed for that? Well, it must be that basically by having multiple processes, each doing a quadrant of the pixel map, it got to get scheduled more frequently by the CPU or by the operating system, I guess. So basically just by having multiple processes, each one taking up a portion of the scheduling of the processor, it got more activity within the schedule cycle. Even though any two of those processes may not have been running in parallel. Basically just think about it. Like, what if there are like 10 things going on the computer, which there might be, right? Who depends on what's running in the background and so on. Um, and so let's say there are 10 things, and only one of them is your program, like the program to write the PPM pixel map. Well, then, maybe depending on how things get scheduled, the first 9 things run, and then your program to process the pixel map gets to run on the 10th call, just for making up numbers, just for demonstration purposes. And then it goes back around in a cycle. The first 9 things run, and then your program gets to do another execution. It's all happening so fast you can barely tell that this is what's going on. But let's imagine that that's what's going on, and so it's kind of slow because you only have one scheduled operation per run through the schedule cycle. Well, if you create multiple processes, even if they're not running multi-threaded, but there's just a bunch of them, now maybe there's 9 things plus your extra 4 processes. And that just means that they get to eat up more time in the schedule, even though they're not running multi-threaded. Well, okay, so that's maybe why we saw gains in computation speed for the program in the previous way of doing this assignment. But now that it's multi-threaded, it's not just that we're eating up more spots in the schedule, relatively speaking, but it's that they're genuinely running at the same time. Like I said, on a single pulse of the CPU, these multiple threads each get to use up resources during that single CPU pulse. So it may cause some gains in efficiency. So I would hope, and if I measured this, I didn't even bother to write the thing, and it wouldn't even take that long, but I really need to get to these other things that I am busy with. But it wouldn't take that long to measure the time, but I just didn't. In any case, you would hope that you would see some increased speed of this program relative to the previous program. But anyway, so you create this thread, it is now running. You create another thread, it is now also running. This is important because if you call, right, what you typically do is you create the thread and then you join that thread. Well, the join is effectively kind of like saying, wait until the thread has terminated. And so that's like a wait, similar to what we saw in the previous implementation. Well, if that's a wait, then if you create and then wait and then create and then wait, right? If you did, all the create and then join and then create and then join, it would be no better than if you had a single threaded program, because you'd be pausing the compute right before you ever got around to booting up or starting the other thread. You'd be pausing the computer, waiting for the first thread to finish before you start up the second thread. Well, what's the point in that? So no, you want to make sure that you do a bunch of creates first, and then only after you've created all your threads, you then join all of your threads. And you want to make sure that you only write to the pixel map, or from the pixel map, I should say. You should only write to the file from the pixel map after all of your threads have finished, which is to say after you've called join on all of them, you write to the pixel map, and when you run this function, so I disabled some of the warnings. I don't know if that would matter here, but in any case, so yeah, so I get, you make, you run. I disabled some of the warning messages, which I don't know if I've sort of satisfied everything that would need, like if I put the warning messages back in, would I see any? I don't know. But the point is, I run this and I open up the generated ppm file, which is here, and look at that, absolutely beautiful, and hopefully runs very fast, having used threads. So very satisfying, very fun. Adios, guys, and I'll see you later.